A stone block sitting at 12,800 feet in the Bolivian Andes was just scanned down to 1/100th of a millimeter, a precision tighter than what most aircraft parts require, and the results are forcing archaeologists to rewrite how they think ancient builders actually worked. This is the real story of Pumapunku's H-blocks and what modern scanning technology just found inside their joints. On a windswept plateau near the shore of Lake Titicaca in Bolivia sits a scattered field of cut stone blocks that has puzzled researchers for over a century. The blocks are carved from andesite and red sandstone, two of the hardest and most stubborn stones found anywhere in the region. Shaped with angles so precise and surfaces so flat that for 120 years, nobody has been able to fully reconstruct what the original structure actually looked like. The site is called Puma Punku. Its builders were the Tiwanaku, a sophisticated pre-Columbian civilization that rose to power in the high Andes around 300 AD. And in late 2024, researchers finally brought a piece of equipment to the site capable of measuring these blocks with a level of precision nobody had ever applied to them before. To understand why that scan mattered so much, you first need to understand what the Tiwanaku actually were. They emerged on the southern shore of Lake Titicaca, the highest navigable lake in the world, and by their peak, between roughly 500 and 900 AD, they controlled territory stretching across the Bolivian Altiplano into parts of modern Peru, Chile, and Argentina. This wasn't a small, scattered tribe. It was an organized, state-level society with advanced agriculture, extensive trade networks, and monumental architecture. Their capital city, also called Tiwanaku, may have held tens of thousands of people at its height. They developed raised field farming techniques that boosted crop yields in punishingly thin mountain air. At elevations where growing food should have been nearly impossible, they produced distinctive ceramic styles that spread across the central Andes and carved massive stone monoliths that still stand at the site today, including the towering Bennett monolith, over 20 feet tall. Nobody seriously disputes that the Tiwanaku were real, organized, and genuinely accomplished. What's been argued for over a century is something narrower and stranger, whether the Tiwanaku's own tools and methods can actually account for the specific precision found at Pumapunku itself. That question matters because Tiwanaku society didn't emerge overnight. Archaeological evidence suggests the culture developed gradually over centuries, starting from smaller agricultural communities around the lake and slowly consolidating into the regional power it eventually became. That gradual development gave the society time to refine specialized crafts across many generations, including stonework, which is an important detail when weighing how plausible it is that later generations of Tiwanaku craftsmen could have developed genuinely advanced techniques passed down and refined over centuries rather than invented from scratch. A civilization with hundreds of years of accumulated stoneworking experience, organized under a centralized state capable of directing large, coordinated labor projects, looks considerably more capable of producing something like Pumapunku than a smaller, less established society would. Pumapunku sits about a quarter-mile from the main Tiwanaku complex, and it looks and feels different from everything else at the site. The main complex contains impressive but fairly conventional architecture, stone walls, terraces, and temples, sophisticated construction that clearly fits within what you'd expect a skilled Andean civilization of this period to produce. Pumapunku is a different animal entirely. Its blocks are cut with a level of precision that shows up almost nowhere else in the ancient world outside a handful of famous comparisons, like the finest Inca stonework at Cusco or specific structures in ancient Egypt, surfaces flat across multiple feet, angles that repeat consistently across separate blocks, almost as if they were produced from shared templates, interlocking grooves and notches that suggest a genuinely deliberate, systematic construction method. And the material makes all of this even more striking. Andesite is a hard volcanic rock, sitting around 6 to 7 on the Mohs hardness scale, noticeably harder than copper, which measures only around 3. Copper tools alone simply cannot cut andesite efficiently. The tool wears down faster than the stone does. Producing a single clean cut with copper chisels alone would take an extraordinarily long time, and would typically leave visible, irregular tool marks from slow, repetitive work. For decades, researchers studying Pumapunku's surfaces kept describing something different, unusually uniform faces, sharp, consistent corners, and grooves that looked almost stamped rather than hand-carved. The first Western researcher to take this seriously was Arthur Poznański, an Austrian-Bolivian engineer who became consumed by the site in the early 20th century and spent over 50 years studying it. Poznański's most famous claim involved astronomical alignments. He argued that certain structures at Tiwanaku were oriented toward solstices and specific stellar risings, and that by calculating the slow precession of Earth's axis backward from those alignments, the original construction could be dated to somewhere around 15,000 BCE. That specific date has been firmly rejected by essentially every modern archaeologist. Radiocarbon dating of organic material recovered at the site consistently places construction between roughly 300 and 900 AD, squarely within the known Tiwanaku period, and Poznański's astronomical methodology has been criticized on multiple technical grounds since, including questions about which specific structures he chose to measure his alignments against, and how reliably those structures had kept their original orientation after centuries of earthquakes and looting. But his raw observations about the stonework itself proved harder to simply wave away. He carefully documented the precision of individual blocks and the complexity of the joinery between them, and later researchers, using far more sophisticated equipment, kept arriving at strikingly similar numbers. Surfaces flat to within 1/1000th of an inch, angles that repeat almost identically from block to block, internal geometries that mirror each other closely enough to raise real questions about how that kind of consistency was achieved by hand. The conventional archaeological explanation for how the Tiwanaku actually shaped these blocks centers on diorite hammerstones. Diorite is a hard stone with a composition similar to granite, roughly comparable in hardness to andesite itself, and the proposed technique involves workers using diorite hammerstones to slowly pound and remove material from the andesite, gradually shaping the block through sustained, repetitive percussion. This technique is well documented elsewhere in the ancient world, including at the granite quarries of Aswan in Egypt, where the famous unfinished obelisk still shows the rough, irregular surface marks left behind by exactly this kind of pounding. The hypothesis is entirely plausible in principle. The harder question is whether pounding alone explains the finished surfaces actually found at Puma Punku, since hammerstone work by itself tends to leave a rougher texture that then requires substantial additional grinding, polishing, and abrasive finishing to reach a genuinely smooth, flat result. That's exactly the gap the 2024 scanning project was designed to close. A European geoarchaeology research team brought a structured light 3D scanner to Puma Punku, a piece of equipment capable of measuring surface irregularities down to 1/100th of a millimeter, roughly a tenth, the thickness of a human hair, and more precise than the tolerances required in modern aerospace component manufacturing. Structured light scanning works by projecting a fine grid of light patterns onto a surface and analyzing exactly how those patterns bend and distort as they cross every bump, dip, and edge. By comparing the projected pattern against what the sensor actually records, the system reconstructs the surface geometry in extraordinary detail, far beyond what calipers, straight edges, or earlier laser measurements could achieve. The team scanned multiple H-shaped blocks, along with several large flat platform elements, capturing both the exterior faces and the intricate internal grooves and corner joints that have puzzled researchers for generations. It's worth understanding why this specific technology mattered so much compared to everything that came before it. Earlier generations of researchers, including Poznański himself, relied on hand tools like calipers and straight edges, instruments capable of detecting variations down to perhaps a millimeter under good conditions. That's genuinely precise by everyday standards, more than good enough to notice that a surface is unusually flat, or that an angle looks suspiciously consistent. But it isn't precise enough to actually characterize what's happening at the scale where the real questions live. A millimeter of uncertainty can hide the exact difference between a surface produced by careful, skilled handwork and one produced by something closer to a repeatable, standardized manufacturing process. Structured light scanning closes that gap entirely, which is exactly why researchers in fields like aerospace and automotive manufacturing rely on the same underlying technology to verify that a physical part actually meets its design specification, down to differences measured in thousandths of an inch. The results confirmed what earlier, less precise measurements had already hinted at. Surfaces measured flat to within roughly 0.005 millimeters across spans of several feet, a level of flatness that goes well beyond what's visually apparent and starts to approach what modern precision grinding equipment produces. Internal corners on the H-blocks met at angles deviating from a true 90 degrees by less than 1/10 of a degree, tight enough that a modern machinist would recognize it as genuine engineering tolerance. Grooves cut into the block surfaces held a consistent depth to within about 1/10 of a millimeter across their entire length, with walls running parallel and floors staying flat rather than wavering the way hand-carved material typically does. Petrographic and mineral analysis of the stone itself confirmed the blocks are naturally formed volcanic andesite rather than some kind of cast or synthetic material, closely matching mineral samples taken directly from identified quarry sites several kilometers away, which put to rest a separate, more exotic theory that had circulated for years, suggesting the blocks might have been poured or molded rather than carved from solid stone. Follow-up laboratory work in 2025, including scanning electron microscopy and thin section analysis under a microscope, reinforced that same conclusion, showing crystalline structures fully consistent with naturally cooled volcanic rock rather than any kind of artificial composite. What the scans also picked up, though, was just as important as the precision numbers themselves, the actual tool marks preserved on the stone. Rather than showing the kind of smooth, featureless finish a machine tool leaves behind, close examination revealed repetitive abrasion patterns, consistent with sustained percussion followed by grinding. Exactly the signature you'd expect from patient stone-on-stone work, combined with a slurry-based polishing process using sand or a similar abrasive. That detail matters enormously, because it means the precision at Pumapunku isn't evidence of some fundamentally different, unexplained manufacturing process. It's evidence of an extraordinarily disciplined version of a manufacturing process archaeologists already understand reasonably well, one that clearly depended on standardized measurement systems, careful planning, and an enormous, well-organized labor investment, rather than on tools or techniques outside the range of what a sophisticated Bronze Age Andean society could plausibly develop over generations of specialized craftsmanship. Researchers studying the H blocks specifically have also picked up on something that looks less like decoration and more like engineering intent. The interlocking geometry of the blocks, where a protrusion on one piece is designed to slot precisely into a recess on another, appears specifically shaped to help distribute stress during earthquakes, which are common across this stretch of the Andes. Simulations of that interlocking geometry suggest it meaningfully reduces shear forces compared to a simpler stacked design, hinting that whoever engineered this specific system was thinking seriously about how these structures would need to survive seismic activity over the long term, not simply about how they'd look when finished. Similar interlocking strategies show up at other sites across the Andes as well, suggesting this wasn't a one-off trick unique to Pumapunku, but part of a broader regional engineering tradition focused specifically on earthquake resistance. None of this makes the site any less remarkable. If anything, it arguably makes it more impressive because it means real people, using real tools available to them at the time, achieved genuinely industrial-grade tolerances through nothing but skill, patience, standardized methods, and an enormous coordinated labor effort at over 12,000 feet above sea level, where the air holds roughly 40% less oxygen than at sea level, and every hour of hard physical labor costs noticeably more than it would down at the coast. Moving these blocks in the first place was its own enormous undertaking. The andesite came from quarry sites roughly 10 miles away across genuinely difficult terrain, while some of the massive red sandstone platform blocks, a few weighing close to 100 tons or more, were transported from sources reported to be over 50 miles distant. Archaeological surveys have since identified graded transport pathways connecting these quarries directly to the Pumapunku site, physical evidence of exactly the kind of large-scale logistical planning that would have been required to move stone of this size across Andean terrain, using sleds, rollers, ropes, and a coordinated, well-managed workforce. It's worth putting that altitude challenge in concrete terms. Modern workers operating at comparable elevations typically tire noticeably faster and need significantly more rest than workers doing identical physical labor at sea level, simply because there's less oxygen available in every breath. That means the actual person hours required to quarry, transport, shape, and eventually place blocks weighing tens of tons, sometimes close to 100, would have been substantially higher at Pumapunku's elevation than an equivalent project built somewhere near the coast. Pulling that off required not just skilled stoneworkers, but an entire supporting logistical system. Enough food surplus to sustain large labor crews over extended periods, a command structure capable of coordinating quarrying, transport, and construction as separate but connected phases of one long project, and enough institutional continuity to keep that effort moving forward across what was likely years, possibly decades, of sustained work. That's exactly the kind of centralized organizational capacity historians already associate with the Tiwanaku state at its peak, which is part of why the emerging picture of Pumapunku fits so comfortably within what's already known about Tiwanaku society, rather than requiring anything beyond it. So if the precision itself isn't the unsolved part of this story, what actually is? The real, still unresolved mystery at Pumapunku isn't how the stone was cut. It's what it originally looked like when it was still standing. Pumapunku has been ransacked for roughly 500 years. Spanish colonizers pulled blocks from the site to use as raw building material elsewhere. Local farmers over the centuries carted off stones for their own construction projects. Earthquakes, the very events this interlocking design was apparently built to resist, still toppled sections of the structure and scattered its components across the plateau over time. Of the roughly 150 blocks believed to have made up the original standing architecture, none remain in their original position today. What's left is closer to a debris field than a ruin, a scattered stone puzzle with a meaningful number of its pieces missing, damaged, or relocated entirely. That's exactly why simply proving the blocks could have been cut this precisely doesn't finish the story. Reconstructing what they originally assembled into has turned out to be its own genuinely difficult, unresolved problem. Researchers at UC Berkeley, led by archaeologist Alexei Vranich, spent years tackling this specific challenge, ultimately taking what might sound like a surprisingly low-tech approach. Rather than relying purely on computer modeling, they created accurate, small-scale, three-dimensional printed replicas of the surviving fragments, scaled down enough that researchers could physically pick them up, rotate them by hand, and test different configurations directly. Vranic has pointed out that the human brain still tends to outperform a computer screen when it comes to intuitively manipulating irregular three-dimensional shapes in space and giving researchers physical models to handle, let them explore possible arrangements far faster than screen-based modeling alone had managed. That project, building on more than a century of careful measurement work by earlier scholars, has produced some of the most promising steps yet toward understanding how these scattered fragments originally fit together, though a fully confirmed, complete reconstruction still hasn't been achieved. The scale of the puzzle Vranic's team took on is worth appreciating on its own terms. Field notes and measurements collected by different generations of researchers, working decades apart with different tools and different documentation standards, had to be reconciled into a single usable dataset before any physical modeling could even begin. Many of the original blocks are simply too large and too heavy to move or handle directly, which meant researchers spent years working from photographs, hand-drawn sketches going back to the 19th century, and painstaking physical measurements taken directly at the site, rather than being able to examine the actual stones side by side in a lab. Turning that scattered, decades-spanning archive of data into a coherent, testable physical model was as much an exercise in historical detective work as it was in engineering. Combine those two threads, the newly confirmed manufacturing precision from the 2024 scans and the ongoing reconstruction puzzle, and you get a much more interesting and more honest picture of Pumapunku than the old impossible ancient technology framing ever offered. The precision is real, and it's genuinely remarkable, but it's explainable through patient, disciplined use of known techniques, hammerstone percussion, abrasive grinding, standardized measurement, and enormous organized labor, rather than through some undocumented lost technology. What isn't fully resolved yet is the assembly itself, which blocks originally connected to what the completed structure or structures actually looked like standing, and how a construction project this sophisticated was organized and managed across however many years it took to complete. There's also a genuinely fascinating structural mystery still sitting underneath the interlocking H-blocks specifically. Even with the puzzle pieces this scattered, researchers have noted that the surviving blocks don't uniformly fit together in an obvious way. Some pair up cleanly, others show slight variations in dimension that suggest either different production batches made to slightly different specifications over time, or simply that too many connecting pieces are missing for the full picture to click into place, using only what survives today. That detail keeps researchers cautious about declaring any single reconstruction final, and it's part of why work on the site continues, rather than being treated as settled. One idea that occasionally surfaces in discussions of the site, and that's worth addressing directly, is whether Puma Punku might have simply been left unfinished, its blocks manufactured and transported to the site, but never actually assembled into a completed structure at all. It's a genuinely interesting possibility, and it would help explain some of the dimensional inconsistencies between blocks that researchers have documented. But there's no clear evidence pointing to a specific catastrophe or sudden historical event that would explain an abandonment like that. The Tiwanaku state didn't collapse suddenly. Available evidence points instead to a gradual decline stretching over generations, eventually fragmenting into smaller regional groups that were later absorbed into the expanding Inca Empire centuries afterward. That slow, unremarkable kind of decline doesn't obviously explain why a major construction project would have been abandoned mid-assembly, so most researchers still lean toward viewing the site as a completed structure that was later damaged, dismantled, and scattered by 5 centuries of subsequent human and natural activity, rather than one that was left incomplete from the very beginning. Zooming out, Pumapunku fits into a much broader, genuinely well-documented pattern in archaeology. Modern researchers repeatedly underestimating what ancient societies were capable of, only to have new tools force a correction. Later scanning of the Central American jungle revealed Maya cities far larger and more densely populated than anyone had assumed possible just a couple of decades ago. Careful remeasurement of Egyptian stonework revealed tolerances that took modern engineers by surprise. In each case, the lesson wasn't that some unknown, undocumented civilization or lost technology was secretly responsible. The lesson was that skilled ancient societies, organized properly and given enough time, patience, and coordinated labor, could achieve results that look almost implausible from a distance, right up until researchers actually measure the evidence carefully enough to explain it. That pattern holds an important lesson for how a site like Pumapunku actually gets studied going forward too. For much of the 20th century, researchers approached sites like this one with tools that simply weren't sensitive enough to distinguish between impressively precise handwork and something that shouldn't be possible with handwork at all. That measurement gap is exactly what let genuine uncertainty curdle into decades of speculation about lost civilizations and unexplained technology, not because the speculation was unreasonable, given the available evidence at the time, but because the available evidence itself simply wasn't good enough yet to settle the question either way. Structured light scanning, petrographic analysis, and physical 3D printed reconstruction modeling represent exactly the kind of tools capable of finally closing that gap, replacing decades of argument with numbers precise enough that different research teams working independently should be able to arrive at the same conclusions. Pumapunku looks like it belongs in that same pattern. The 2024 and 2025 scanning work hasn't uncovered evidence of some undocumented predecessor civilization or a mysterious lost manufacturing process. What it's actually done is confirm, with far more precision than ever available before, that the Tiwanaku were considerably more sophisticated stoneworkers than they're sometimes given credit for, organized enough to standardize measurements across hundreds of separate blocks, patient enough to grind and polish, andesite to genuinely engineering-grade tolerances by hand, and thoughtful enough to design interlocking joints specifically to help their structures survive earthquakes in a seismically active part of the world. The real mystery left standing on that windswept Bolivian plateau isn't how they managed to cut the stone. It's what the finished structure looked like before 5 centuries of looting, farming, and earthquakes scattered its pieces across the ground, and how long it might take researchers, working piece by careful piece to finally put it back together. That's ultimately what makes this an ongoing story rather than a closed case. Every new scan, every additional fragment properly cataloged and measured, and every refinement to the physical reconstruction models brings researchers a little closer to answering the question that's actually still open here. Not whether the Tiwanaku were capable of producing something this precise, since the evidence now strongly suggests they were, but what, specifically, they built with that capability, and how it all originally stood together on that plateau before time, weather, and centuries of human hands slowly took it apart. For now, the blocks remain exactly where 500 years of upheaval left them, scattered across a windswept plateau at 12,800 feet, their surfaces holding tolerances tight enough to satisfy a modern machinist. Their original arrangement still an open question. The precision has finally been measured. What it once formed is still being pieced back together, one careful scan and one printed fragment at a time.